Okay, we want to talk about transformations of graphs. We want to talk about a stretching transformation from a geometric point of view. So we have a graph here of y equals f of x equals x to the p for some unspecified power p. We don't care what the power is. Okay, we can see the 3 points pretty much from these dots that I used to construct this graph. But what we want to do is we want to take the y value of each point on the graph and increase it by 25%. Okay, we want to make it 25% greater. Now, how can we do that? Well, let's just pick this point here. Of course, the y value is here. Okay, now 25% is 1/4. And we can actually construct this geometrically. We can use a straight edge and a compass to bisect the interval from here to here, and then to bisect that interval. So if we bisect the interval twice, we're going to get a value here, and we're going to get a value here. So this value should be 1/4 of this y value. So, and we could do this over here on the y-axis if we wanted to. Okay, we could bisect this interval and then bisect again. 1, 2, 3, 4. I don't have that quite right, but we get the idea. Then I could set the compass between this point and this point, come up here, set the point of the compass here, and the lead here, and I can mark that point. Okay, and I maybe mark a little bit of an arc here, because that's what we do with a compass inevitably, and then take the straight edge and come straight up here. Okay, now various ways we could use the compass to make sure this point is located as accurately as we can locate it with our compass. In any case, now the y value here is now 25% greater than it was. So here's our y value. Make that a kind of a white dotted line. And then %, greater. I had to abbreviate that to leave myself enough room here. So right there is a new point, a point on the graph of g of x. Now, all we have to do is do that for every point on this curve, all the way out to infinity, and we'll have our graph of g of x. Naturally, that's not feasible. We don't have time to do all the points, so we'll just do a few of them, just to get an indication of where the graph would be. Well, we can apply the same procedure here. We can cut this interval in half, and I'm not going to do projection lines. Things will get even messier than they are. But I think we have this, and I think we have this. So I think we've got to add about this much, which is going to put us about here. And we can do the same thing here. Half is there, a quarter's about there, so we're going to add about this much. So we're going to go about this much higher. And here, a quarter of that's here, so we're going to go to about here. So now we have a series of points on the graph of our g of x function that's defined as the function we get if we do this construction on every point of the graph of the x to the p function. And of course, if we increase the value at the origin by 25%, well, the value at the origin is 0, 25% of 0 is 0, so we're adding 25% of 0 to 0. We're going to get 0, aren't we? So now we have this graph of g of x. Okay, so I'm going to ask a couple of questions just to focus our attention on this graph, it appears that the graph of g of x keeps getting further and further away from the graph of f of x. So why does the graph of g of x keep getting further away from the graph of f of x? As x increases. Because of course, if you think the graph start out here and move this way, the graph is getting closer, right? So for increasing x, why does the graph of g of x keep getting further and further away from the graph of f of x? Okay, then what's the formula for g of x? G of x equals what? Okay, well, f of x equals x to the p. So I'm going to reason this out as follows. %25 more than y is y plus 0.25y, isn't it? And that equals what? Well, we could factor out y, and we get 1 plus 0.25. So that's 1.25y. Okay, so if y equals x to the p, and I don't want to say it that way, I'm going to do something I don't like to do much of, which is make a correction in front of the camera. So if y equals f of x, %25 more than y is what? Well, it's 1.25 times what y was. Which is 1.25 times f of x. Okay, so it follows that g of x has to be 1.25 times f of x, which is, of course, then 1.25x to the p. So I can say then, because of this, the g of x is 1.25x to the p. Now what we've done is we've vertically stretched the graph of f of x by a factor of 1.25 to get g of x. So vertically stretch the graph of f of x by factor (1.25) to get the graph of g of x. When we vertically stretch by a factor, then as the y value of a function increases, the y value of the stretch function also increases. If the stretching factor is positive, the y value of the stretch function will also increase, and it will increase by more and more as the value of y gets bigger. Now you want to think through exactly why that happens and write out exactly why we can say that the graph of g of x in this case will keep getting further and further from the graph of f of x.